All right, let's take a look at another example. In this one, we have a truss instead of a loaded beam, and we're going to take a look at its external forces. It's got a pin joint here and a roller joint on the other side here. And if we remember, a pin joint gives us two reaction forces, and a roller joint gives us just one perpendicular to the ground. So the first thing that we're going to need to do to solve this guy is going to be drawing a free body diagram. Okay, so our free body diagram is going to look a little bit like this. Okay, and then we're going to replace our joints here with some reaction forces. So remember, we have a vertical reaction force and a horizontal reaction force for our pin joint. We've got just a vertical reaction for that roller joint, and then we've got F1 here and F2 over here. So since F1 is going down, I'm just going to assume, and let's label these guys so we know what we're looking at here. So I'm going to assume that RD in the y direction, so that's our reaction force at joint D in the y direction, is going to be going in the up direction, or the positive y direction. And we assume that just because F1 is going down. So the same thing, I'm going to make that same assumption for RAY. I'm going to assume that that guy is going up as well. And then if we're looking at RA in the x direction here, I'm going to assume that this is going to the left or the negative direction, because F2 is going in the positive direction. So I'm just going to assume that that guy is going that way. All right, now that we've got our free body diagram, the next thing that we're going to want to do is we're going to want to sum the moments around any point P, and we're going to set them equal to 0. Okay, so when we do that, we should be able to solve for some of our stuff. So if you remember from the last video, we said that 90% of the time we're going to set our moment around a pin joint, because that's going to make our lives a little bit easier. So we're going to set it around A. So if we're setting it around A, we could have the moment caused by A in the x direction. We could have the moment caused by A in the y direction. We could have the moment caused by F1, and F1 is going to try to rotate us in a clockwise fashion, so that guy's going to be negative. And if you don't remember, we can draw our coordinate system here. Remember, this was positive x, this is positive y, and counterclockwise is our positive moment. So we assume that F1, and that means also the moment caused by F2 is going to be negative, and then our moment caused by dy is going to be positive. Okay, so remember, moment is equal to your force times your distance in the perpendicular direction. Okay, so our distance for AX and AY is 0. So these are both going to be equal to 0. Our force for F1 was 600 pounds. So 600 times our distance, which in this case is 24. The distance between C and D is 8, and the distance between C and B is 12. Okay, so this is going to be 600 times 24 minus the moment of F2, which if you scroll back up is 500 pounds. So 500 times the distance here is 12, because that's the perpendicular. This is the distance is perpendicular to this force. Okay, so if we go back to that, it's going to be 12, and this is plus 32. That's 24 plus 8 r dy. Okay, so if we are setting all that equal to 0, we have 0 is equal to 600 times 24 is 14,400. Or minus 500 times 12, which is 6,000. And then plus 32, so that's a minus here also. Plus 32 times r dy. So we get 32 r dy is equal to 20,400, which gives us an r dy equal to 637.5 pounds. Okay, so that is the first reaction solved for. So r dy is equal to 637.5. Okay, so let's grab a new page here. And the next one that we're going to do is we're going to sum our forces in the x direction. And then remember those, since this is equilibrium, it's going to be equal to 0. In this case, we had two forces in the x direction. We had F2, which is going in the positive direction, and then we assumed that RAX was going in the negative direction. Okay, so F2 is equal to 500 minus RAX. That's all equal to 0. So that means RA in the x direction is going to be equal to 500 pounds. Okay, so that's our second reaction force solved for. And then the last thing we've got to do is sum our forces in the y direction. That is also equal to 0. For this one, we had three reactions. We had 0 is equal to, we had RAY, which we assumed was going in the positive direction. We had F1, which is going in the negative direction. And we had RDY, which is going in the positive direction. Okay? So we have 0 equal to RAY. F1 was 600 pounds. And RDY was 637.5 pounds. So if you do some math, that gives you RAY is equal to negative 37.5 pounds. Uh-oh. We've got a negative number. We're not supposed to have negative forces here. That's okay. That just means that we drew our free body diagrams incorrectly. So we made an incorrect assumption. So let's go ahead and redraw our free body diagram here really quick. Look at this guy. So we had F2 going this way. We had F1 going this way. This was R dy. We had RAX. And then instead of in the positive direction, we just need to draw RAY in the negative direction. Okay, and that fixes our free body diagram. So this was just a pretty quick example of how you could solve for the external forces on a truss given, or solve for the reaction forces, the external reaction forces of a truss given some other forces. Okay, so like always, if you have any questions, please feel free to let me know.